Let's solve a live problem on partial fractions, and in this case we're going to talk about or solve type 1 linear factors non-repeating, and this kind of an exam problem which is very common in all the exams. So let's talk about that. In the last episode we did understand some of the intuition which will refer back on what exactly was happening all along the journey between a rational expression and a partial fraction, and we had key observations, and let's try to apply some of those observations into the live problem for solving. And for sake of convenience, whatever example we took in the last episode, I'm taking the same example and breaking it down. And again, as a reminder, this is an exam problem. Let's talk about that. Okay, so what do we have here? So we have a given problem and we need to solve. This is a rational expression that we have got, and it says resolve into a partial fraction. That means convert this rational expression. This is a rational expression which is a ratio of two polynomials in the denominator and the numerator, and convert this into a partial fraction. That's our equation. That's our objective. Okay. And before we start the problem, if you remember in one of the episodes where we spoke about factorizing polynomials, we spoke at length about the three important checkpoints. Does not matter whether we are solving type 1 or type 2 or type 3 or any other problem. We need to have, as long as we are trying to solve a proper fraction, regardless of the three types, these three checkpoints we need to always do before we start solving the problem. And what are those? The first checkpoint is to check if the given fraction is a proper fraction or an improper fraction. And since we know that we are dealing with only proper fraction for now, for all this type 1, type 2 and type 3, we know that it's a proper fraction, but we can always check the degree. The degree in the numerator is 1, over here x to the power 1, and this is numerator and this is denominator, and the degree in the denominator is quadratic equation, and hence the highest degree is 2 and 1 is less than 2, and hence this is a proper fraction. We already know that. Okay, this first checkpoint is done. Okay, what is the second checkpoint? We have to check whether we can factorize specifically the denominator, and we can simplify the expression into a lower degree or maybe linear factors. So in this case we have got a quadratic equation, and can we simplify that? In some cases we can simplify, in some cases we cannot simplify. So if we can simplify this in step 2, we have to simplify and break it down to a lower degree or the simplest form. We need to bring it as close as to a linear expression, meaning x to the degree 1. And the third checkpoint is sometimes factorization is not possible. For example, there could be a crazy quadratic equation like, say, we have x squared plus 4, where the factorization is not possible, which is what we'll see in type 3. In that case, we do not do anything, we just keep it as it is. Okay. Now, in this case, let's check the step number 2, whether the factorization is possible or not. And I've kind of done a little doodle here. So the denominator is x squared minus 2x minus 3. I've taken it here, and we're checking, can this be factorized? And looks like this can be factorized because we can do two factors, x plus 1 and x minus 3. And if we just cross multiply and open up the brackets and simplify, we still get this expression over here, x squared minus 2x minus 3. And hence x plus 1 and x minus 3 are the two factors for this particular polynomial, and it can be factorized. So it's a good check, and we have already checked that. And just a reminder, how do you factorize it in case you don't remember? I've already explained this, and this is basic elementary stuff in quadratic. You take the equation, and we have to find two numbers which when multiplied will give the constant, which is minus 3. So the two numbers are minus 3 and 1. When you multiply that, we get minus 3. And we have to find this, and the same two numbers, when we add or subtract, it has to give us minus 2 in the middle term. Okay, and if we take the same two terms or same two numbers, we get minus 3 plus 1, and when we do this, we get minus 2. So since we are able to do this, we can find those two mysterious numbers. That means this can be factorized, and those becomes the factor in terms of x plus 1 and x minus 1. That's a little recap on what we do. Okay, we have done this. The first checkpoint is through, the second checkpoint is through, the third is not applicable because step 2 we have done, it's factorized, so we can skip the step 3 directly. Now let's see what we can kind of do here. The most important step is this particular step, which is in this box, which I've highlighted as most important step. And what is this important? So what are we trying to do here? We are trying to take the given rational expression, which is this example. We are trying to take that. We know that it can be factorized, which is what we have factorized it here. And we know partial fractions is all about finding these constants, and we are expressing them in this constants, where we are expressing this whole rational expression into a partial fraction for now with this unknowns a and b, and we have simplified into two linear terms. Okay, we have simplified into two linear terms. And why we have taken two constants and why this structure, the whole crux was explained in the last episode, where we spoke about these observations on why, how things shape up. But the two main observations that you need to remember is, for type 1 linear factors, non-repeating. So if you see, once you factorize the given problem, you see that over here, let me just erase this and create some real estate. If you see here, we can easily identify, after factorization, we can easily identify the terms are non-repeating and the terms are linear, which is type 1. Okay, because the power is 1. And whenever we have type 1 and linear equation, we have seen in the previous episode that we can keep the denominator the same, but we can separate out the terms, which is what we have done for each term. And the numerator will be just constants because the factors are linear, x to the power 1, and we have to get a polynomial in the numerator with a lesser value than this, one value less than this, x to the power 0. That's what we saw here, which is as good as not writing the polynomial, because even if you write a x to the power 0, it just means a, and b x to the power 0 is just b. So it is as good as you don't write anything here and just leave it as it is, and that's where this constant came. So the trick in the step is identify the type after factorization. In this case, we know it's type 1 non-repeating linear factors. If that's the case, we straight away take each factor in the denominator, separate them out. In the numerator, we put the constants that we need to find, and it can go as long as we want. We can say a, b, c if there are more terms. And the trick is, since it's a linear factor, the degree is always going to be 1 less than the denominator, because we don't want to make this as an improper fraction. And then we just continue in the descending order. In this case, there is nothing to descend because there's only one term and we cannot go any further. So that's the two tricks, right? Identify the type of the problem, and based on that, if it's non-repeating linear, simply separate out the denominator for each term and substitute by the constant, and then we do the simple maths to find the value of a and b, which is what I have shown here. So what we have done here, so now we have simplified. We have taken 2x plus 3 and this equation, which is the factorized denominator, and over here we just cross multiply using simple maths, because we need to have the common denominator on both the sides. So we just cross multiply, and once we get this step, we just cancel out the denominator over here. We just cancel out the denominator over here. We don't want this, and just keep the numerator from this particular equation. If you see now, we have got 2x plus 3 is equal to a into x plus 1 and b into x minus 3. Now the trick is, how do you find the values of a and b, because that was our whole objective to get the partial fraction. And it's very simple, right? So there are two ways to do that. I'll talk about the substitution way in this, and in the next episode there's another way called as equating the coefficients, which is another way to do that, and you can pick up any way, whichever you want to do it. In some cases this might not work. This is the easiest way, so you have to pick up the other way, but we'll talk about it in the next video. In this case, what do we do? Okay, we need to find two unknowns here, a and b, and the unknown variable is also x. So what do we do to find a and b? First we make one of these values either a or b 0. And how do we make? We see whatever value is here and we just substitute that value to make this product 0. For example, to find a, we make b 0. And how do we make b 0? If you substitute here plus 3, if you substitute here plus 3 in the value of x, so it becomes 3 minus 3 is equal to 0, and then b automatically becomes 0. That's what we see here. And that way we have substituted the value of x, b has become 0. So this becomes one equation and one unknown, where a is the unknown, and we find the value of the a by simple substitution, where a is equal to 9/4. Okay, that's what it is. And for finding b, what we do is, sorry, I think I erased this by accident. Okay, it was a and this was x plus 1. Was it x plus 1? Yeah, it was x plus 1. Okay. And for finding a, what we do is we take the same step here. If you see here, I'm taking the same step here. And now we need to make a is equal to 0. So we substitute x is equal to minus 1, because if we put x is equal to minus 1, the a terms becomes 0. We have the value of x, which is minus 1. So it again becomes one equation, one unknown. This time we are finding b, and the value of b is minus 1 by 4. So now we have the value of a, now we have the value of b, and we just simply need to copy this values and put it back in this equation, and that's our final answer where we get this answer. So we had the rational expression as this. We simplified using factorization. Then we used a partial fraction in this format for type 1, and we did the magic to find the value of a and b. So this is our final step. So don't forget to write this step, because this is the closing step to get the marks, where you simply write the value of a and b and put this. So that's how you solve most of the partial fractions. In this case, we discussed type 1. And like I said, I'm going to repeat for the last time. What did we do here? Since we factorized, we know that this belongs to type 1, non-repeating linear, where the degree is 1. Okay, we know that. And for whenever we have those cases, what we do is we still need to take all of the denominator and separate it out, like we separated here for each term. And the numerator will be substituted by just a constant. It is as good as the constant multiplied by a to the power 0, because we still need to make it a proper fraction. And even if we don't write a to the power x0, it's fine. So we don't write it. And then the whole objective is to find this constant a and b by simple substitution, where you take any random value of x to make one term 0 and find the other term. And last but not the least, you put it back in the equation, and this way you conclude the answer and you secure your marks. So that's all partial fractions is all about. Doesn't matter which type you solve, starting from a rational expression over here and decomposing it to simple terms like this over here. And this whole piece that you saw, the substitution, the first step that you saw, for each of the type of the partial fractions, how do you define this is the most important step. Once you do that, rest of the piece is a cakewalk. You don't have to do much. The whole point is based on the type of the problem, whether it's a type 1, type 2 or type 3, how do you kind of come up with this equation? Because you'll see in type 2 this will slightly change, and in type 3 again it will change, but the principles remain the same. So how do you come up with this, the very first step, the most important step of forming an equation and then solving it is the other piece. Okay, so this is the most important step for this thing, and this is what you need to learn. How do you kind of map this to the type of problem? And the more you solve, the more you know and how to do the tips and the tricks. So that's a wrap up on this particular example of solving type 1 linear factors non-repeating problem for partial fractions, and we took a proper fraction example. I'll see you in the next type 2 for repeating linear factors. Till then, stay tuned. I'll see you in the next episode.